Okay, let me do this question. Again, this is one of the projectile motion questions of which we have lots of examples of. This is one of those. Let me just do this so that if you got stuck on a question that's similar to this, you have this homework help video. So the question says a golfer on a fairway is, okay, I gotta start drawing, and I think green is below the level of the fairway. Okay, yeah. So there's some, I'm gonna deal with like two different levels. There's one level here, that's the fairway. I don't know what that is, but you don't need to know. All you have to know is that it's kind of a projectile motion. So there's a golf ball that's going to be launched by being hit at an angle of 40 degrees, or let me call that theta for now, with some initial speed, that's 22 meters per second. Let me call that v now for now. And the fairway is about 70 meters away from the green. So this is green. I have no idea what that's referring to, but it must have something to do with the golfing. And well, so it's saying 70 meters away from the green. Let's say there's some sort of reference point on green. Let me call this my x equals 0. That's the point I'm trying to get to. And the golf hits the ball at an angle, yeah. And then, so I guess I should kind of imagine it doing this way. And in order to make the problem solvable, I'm gonna assume that ball doesn't do this. Like in a physical setup, that might be possible, but I think that makes a problem more complicated than it's meant to be. So I'm gonna assume it clears the fairway and it's gonna be level with the green. So there's some sort of let me call this delta y that you can assume. So I'm gonna say this is my y equals 0, and I'll say the ball ends up at y equals minus delta y. So I'll assume that so that the problem is solvable. All right, so the question asks, how close to the green does she come? So in my reading of the question, what that reads to me like, it's asking for the x position, especially if I set up my system this way. I already set x equals 0 here. I can say my initial x position is minus 70 meters. Then wherever it lands, assuming if it's negative, then whatever my x value is, its absolute value should be what they are looking for, the L value. And I guess it's possible for this to go over this reference point here, then it will be, again, the absolute value. So let me give that a try. Now, this is projectile motion question, and that whenever you identify a question being a projectile motion question, there are two things that's very useful to have done. One is to, I guess I kind of implicitly did already, break your motion into x horizontal and y vertical components. Especially like if you have an initial velocity, there will be an x component of that, there will be an y component of that. So this is v naught x, this is v naught y. And the reason doing that is useful is because the equations that govern projectile motion, they are broken out this way. Horizontally, it's super simple. Horizontally, the acceleration is 0, and that leads to your x position being simply determined by your initial position plus whatever the initial velocity is in the x direction times time, and then that's it, because your initial x velocity is also your velocity for the entire motion. Now, in the vertical direction, there's more complexity, but it's still fairly well determined because you know the vertical component of acceleration. It's minus g, gravitational acceleration downward. So that leads to these two equations. You can say your y component of velocity as a function of time is given by the initial y component of speed, which will now be changing, minus g times t from the acceleration in the y direction. And you can say the y position is given by the initial y height plus the change in the position that's attributable to the initial velocity in the y direction times time. Now the portion that's attributable to the y component of acceleration, gravitational acceleration, or minus 1/2 gt squared. And I think for this question, I don't think I will be using this particular expression. So let me cross it out, but it's still useful. Or let me not cross it out, I just won't use it. So it asks how close to the green does come, so you are looking for this. So you know you are eventually going to end up using this equation. Now the problem is you have two unknowns. You don't know the time at which the ball lands on the same plane as the green. So time is an unknown, and final time, of course, you are looking for it. So I'm eventually going to get to equation 2, but I need to find another way to get the time information. And oftentimes in projectile motion, when you need the time information, usually the y component of motion will give it to you. So depending on the condition set up here, I know what my final y height will be. So from this, I can get time information. Sometimes if you're looking for like the top of the trajectory, then you might use the speed equation, velocity equation. But here, let me call this equation 2. So I'm going to solve equation 2 for time and plug it in here to get the x position. So from 2, let me plug in all the numbers. I have y position at the very end is going to be minus delta y from how I set things up. And from how I set things up, initial height is 0. And then plus upward velocity. So I need to use so ka toa to help me write out the y component of velocity. So from so, which means sine of the angle is the opposite v naught y over the hypotenuse v naught. From that I can solve for v naught y is v naught sine theta. So I'll use that. My y component of velocity is v naught sine theta, and it's upward, so it should be positive, times time t minus 1/2 gt squared. Okay, looks like I'll have to use quadratic formula, so I'll do that without too much complaining. Let me put this here. Maybe here. Okay, or actually here. Yeah. All right. So let me first put this equation into the standard form. So I'm gonna move just everything to the left hand side because then I can identify coefficients a, b, and c. So I have 1/2 gt squared, having moved this, minus v naught sine theta t, having moved this over, and I still have minus delta y is equal to 0. This is my coefficient a. This with the minus sign is my coefficient b. This with the minus sign is my coefficient c. And quadratic formula tells me, or let me do it this way. Let me use all from alpha. So I can do it this way. Solve 1/2 times g, 9.8 times t squared minus v naught, 22 meter per second times sine of 40 degrees times t minus delta y, 17 meters. All in basic SI units, say that's equal to 0 for t. All from alpha does some level of natural language processing, some level of computer algebra system stuff. So it'll understand that and it'll solve it for you. And let's do approximate values, approximate forms. Yeah. So negative answer, that's sort of that's from this hypothetical trajectory that didn't actually happen. Like if the ball came from over here, then this is my negative time. I can ignore that, unphysical. So let me just keep the positive time, 3.7992, and I can plug it in here to get my x position. And let me write out the expression for the x component of the velocity from ka, cosine is adjacent over hypotenuse, or cosine theta is the adjacent v naught x over v naught. So my v naught x, solving it for v naught x is v naught cosine theta. And sometimes people get into this habit of always associating cosine with x and sine with the y. Especially when we get to forces, you will want to go through this exercise every single time. Draw the triangle, identify the angle, and go through the SOHCAHTOA exercise. So from that, I can get v naught x. Think of the rest I can do from alpha. Let me just get a new screen, and then I'll 3.7992. So 3.7992, that's my time, times the v naught x, that's gonna be 22 meter per second, times cosine of 40 degrees. And then my initial x position is minus 70 meters. Just adding that in. And then that'll give me my x position minus 5.97. So the golf ball is 5.97 meters away from the 70 meter mark. So 5.97. And that's it. You can also, do quadratic formula. Let me write down quadratic formula in case there are people who are interested. So the quadratic formula says t is equal to minus b plus minus square root of b squared minus 4ac. It's a kind of the balancing thing you have to do, divide by 2a. Balancing thing in the sense of you should know how to do these things by hand. But once you know how to do it, then sometimes, this is kind of... so I believe your goal should be for solving something like this to be tedious. As in, you know how to do it, you can do it. It's a matter of spending a minute or two just writing down the expressions. If we use computer algebra system or computerized tool, it's a little bit quicker. You can do it in 15 seconds instead of 2 minutes. Then you use this as a time-saving device. That I think it's totally fine. That's why in this class you are always allowed to use Wolfram Alpha. And other computer algebra system you will see me demonstrate like a SageMath. But those computerized tools, it shouldn't replace your ability to do these questions yourself by hand, as I demonstrate in other projectile motion questions.